In this lesson, we're going to learn how to simplify radical expressions. First of all, it is very important if you know your perfect squares. This will help you simplify radical expressions because we are not using a calculator. So our perfect squares is when we multiply a number by itself. So we need to make sure that we have this list 4 through 61. All of these are perfect squared numbers. Now let's take a look to see what a square root is. So a radical expression has an index, which is a small little number that's located right here. We have the radical symbol, and then we have the radicand, which is the expression under the radical symbol. Now we always have to have a positive integer for our index, and a radicand has to be a real number. So let's talk about square roots and cube roots. And for this course, we will mainly be looking at square roots and maybe a few cube roots. You can have a fourth root, a fifth root, and so on. It's just how many times a number was multiplied to get that product. So a square root has an index of 2. However, most of the time when we take the square root of a number or expression, we don't write in the index of 2. So this is an understood 2 here, but we do not necessarily need to write it in. So if you see the square root of like 16, you know that we're taking the square root, not the cube root or the fourth root. It's understood to be a 2. And the 2 or the index is right here. It's not the coefficient. It's not a large number. It's kind of like an exponent. It is actually part of an exponent. So the radicand on square roots must be positive. So square roots, this radicand has to be a positive number. On cube roots, they have an index of 3. So it was some number multiplied by itself 3 times. And then we're just undoing that cube root to get back the root. Now with cube roots and any odd roots, you can have a positive or negative radicand. But like I said, we're going to focus mainly on square roots for this course. Now, what does taking the square root even mean? So let's talk about inverse operations first. So how do we undo addition? Well, we know we undo addition by subtraction. Okay, so addition and subtraction are inverse operations. How do you undo subtraction? Well, you add. So addition is the inverse of subtraction. How do we undo multiplication? So it's like 2 times what gives us 10? Well, to undo the multiplication, we know division is the inverse. And lastly, what is the inverse operation of division? How would we solve this? Well, we would use the inverse operation of division by multiplication. And 20 would be our solution. So let's take a look at squaring and the inverse operation. So here we have 6 squared, and we know that that is 6 times 6, which gives us 36. Well, if the question was, I want to undo this squaring, to undo something squared just means to take the square root. So if I take the square root of any of these equivalent expressions, you're going to get back the root, the original base. So the square root of 6 squared, and remember there's a little 2 here, so it's kind of like these cancel each other out, and I get 6. And here, the square root of 6 times 6, to get back that single answer, I get 6. And then when I undo 36, it's the same thing. I'm taking the square root, and I get 6. So all of these are equivalent expressions. So you can see that taking the square root undoes something squared. So let's say that I have 7 squared. And if I take the square root, taking the square root undoes the squaring, and I get 7. Typically, we would see it written out as 49, and taking the square root of 49 gives me that base of 7. What if we had some number squared, just some number, and I said, okay, I want you to take the square root. Well, you use the radical symbol, you take the square root, and you get back x. Let's say I had x to the fourth, and I said, take the square root. Well, we could break this down going back to our exponent rules, the product rule. We could rewrite this as x squared times x squared and just make an equivalent expression. So everyone agrees that x squared times x squared is the same as x to the fourth. And again, I have a little index here. So these twos are going to cancel. So I'm going to take the square root of x squared. That gives me x. I'm going to take the square root of this x squared, and that gives me another x, which gives me x squared. So let me sum that up. The square root of x to the fourth is x squared. Let's do one more and then we'll move on. Let's say I have x to the sixth. Let's rewrite this. This is really, I'm just making perfect squares here underneath my square root. So x squared times x squared times x squared is the same as x to the sixth. Now I want to take the square root of each of these factors. So when I take the square root of x squared, I get x. When I take the square root of x squared, I get another x. I'm bringing it on the outside of the radical. And then I take the square root of x squared, I get another x. So I get x cubed. Okay, let's move on and let's look at the checklist, because not all taking the square root of all expressions are perfect squares. And so that's what this lesson is really about, is taking the square root of a radicand that is not a perfect square without using a calculator. So here's the checklist. To know if my answer is totally simplified, the radicand cannot have any perfect square factors. And we'll go deeper into this. But I can see here this square root of 8, it's not perfect, but I can simplify it, but it is not simplified at all. So I can see, and again, we will learn this in just a few minutes, but if I break this apart, I can see that this 4 is a perfect square, and that's why this is not factored, because I can take the square root of 4. The radicand is not a fraction. We cannot leave this as a fraction, and we'll learn how to simplify. You need to make sure you write this in your notes. You can never have a radicand in your denominator. That is just the same as having like a 0 in the denominator. You can never leave a radicand in the denominator. The last check mark is there are no exponents under the radical greater than the index. So remember, my understood index here is a 2, and this exponent, if it's larger than the 2, I know I have not simplified it. And again, we're about to learn how to simplify these. So let's start with the square root of 48. And again, like we said at the beginning, you need to know your perfect square list. Now, 1 is a perfect square, but that's not going to help us. So I always like to write out the first several numbers of perfect squares. We have 4, 9, 16, 25, 36, 49, and for now, we'll stick with that. So we're trying to rewrite this square root of 48 into two factors in which one is a perfect square and preferably the largest perfect square. So let's rewrite this, and we're going to find the largest perfect square factor. Now 4 can go into 48 times 12, but there's a quote unquote better factor that we can choose, and that's 16. It's larger than 4. It's like simplifying factors. You're going to use the largest common factor to simplify. The same with radicals. So 16 times 3 is equivalent to 48. Now we can see that we can take the square root of 16. So we can undo what was squared to give me 16, which is 4. So we bring the 4 on the outside of the radical, and we're left with square root 3. So we say 4 times the square root of 3. or 4 root 3. And now this is simplified. So to make sure it satisfies all the checks, 3 has no perfect square factors. It is not a fraction. There are no radicals in my denominator. I haven't understood 1. And then here, my exponent on the 3 is 1 and my index is 2. This exponent is not larger than the index, so I'm good to go. Okay, let's try a few. Again, you need to know your perfect squares. This is going to help a great deal. So let's write square root of 24 into an equivalent of fraction. So we know that 4 can go into 24, 9 cannot, so we're good to go. So we're going to rewrite this in 4 times 6. We're not going to use 3 times 8 or 2 times 12 because none of those factors are perfect squares. So this is why we're choosing this set. We're going to take the square root of 4. So we're undoing what was squared to give me 4, which is 2. Square root of 6. And now we have simplified the radical. The square root of 50, we can see that 25 can divide into 50. 25 is a perfect squared number. 25 times 2 gives me 50. The square root of 25 is 5 root 2. Now let's take a look when we already have a coefficient on the outside of our expression. So we have 5 times the square root of 12. Bring down your 5. Rewrite 12. 4 goes into 12. And 4 is a perfect squared number. When I take the square root of 4, I get 2. And I'm going to multiply it by the coefficient that's already out here. So times 2, that gives me 10 roots of 3. Now we have a coefficient of negative 3. I'm going to bring it down. I'm going to rewrite 32. Now, once you do these over and over, you'll start to realize real quickly what the best two factors are. So 4 can go into 32, 4 times 8. But there's a better one. Let's do 16. So 16 times 2 is 32. When I take the square root of 16, I get 4. So I'm going to multiply negative 3 times 4, and I get negative 12, square root of 2. Okay, now our coefficients are going to be rational numbers, fractions. No big deal. Bring down your 1/3. So what times what gives you 27? Well, that's 9 times 3. So and 9 is perfect square. So when I take the square root of 9, I get 3. So 1/3 times 3 times the square root of 3. So I can see that my 3's in my coefficient cancel, leaving me with 1. No need to write the understood 1 out here. And so I get the square root of 3. Now we have 1/4. We're going to break down 8. 4 is a perfect square and it divides into 8. When I take the square root of 4, I get 2. So I have the 1/4 times 2 times the square root of 2. And so this time I'm going to cross simplify. So 2 goes into 2 once and 2 goes in 4. 2. 1 times 1 is 1. 2 times 1 is 2. So 1/2 times the square root of 2. Now let's take a look when we have variables. So no big deal. I'm just going to rewrite this. We know 8 can break down into 4 times 2. I'm going to rewrite these into perfect squares. A squared is perfect. B to the third can be broken down into B squared times B to the first. So I'm just rewriting an equivalent expression. Now I'm going to take the square root of 4. I get 2. I'm going to take the square root of A squared. That gives me A because taking the square root just undoes something squared. When I take the square root of B squared, I get B. And now the radicand is 2B. Let's break down 24, A to the fourth, B to the first. So 4 times 6 is the factors we're going to use because 4 is a perfect square. Now we're going to break down A squared into perfect squares. So A squared times A squared gives me back my original factor times B to the first. We're going to take the square root of 4, which is 2, A squared, which is A. The square root of A squared is A. And I'm left with 6B. Okay, let's put this a times a together, and I get 2 times a squared, 6b, the square root of 6b. Okay, let's do 2 more here. Okay, 72. I immediately want to say 9 times 8. 9 is perfect square. However, when we say 9 times 8, let's just say we did do 9 times 8. If I take the square root of 9, I do get 3, square root of 8. But is 8, this is on that checklist, is 8 completely factored or simplified, I should say? No, because I can see a 4 embedded in this 8, and 4 is a perfect square. So we can say, and we can keep going, just like simplifying fractions if you don't choose the greatest common factor. So if I broke this down again, you can see I have this 4 that's a perfect square. The square root of 4 is 2 times 3 is 6, roots of 2. Okay, so that's fine, but sometimes we may just move on and not realize this is not totally simplified. So always just see if more factors, more perfect squares can divide into your radicand. So let's keep going. So I would just say that 36 does work since I've been doing this a while. So we're going to say 36 times 2, and then we have a squared times a times b squared times b squared. And let's extend that radical. Okay, let's take the square root of 36. This gives me 6. The square root of a squared gives me a. The square root of b squared gives me b. And the square root of this b squared gives me b. And I'm left with a radicand of 2 times a. And let's put our b's together as one factor. And that's our final answer. 40. I can see 4 times 10 is 40, and 4 is a perfect square. A, b. And the only perfect square in my radicand is a 4. So when I have 2 times the square root of 10, AB. Now you pause the video. When we come back, we will go over these. And remember, no calculator. Okay, 54. We're going to break this down into 9 times 6, 9 being a perfect square. That gives us 3, square root of 6. 108. Again, once you do these for a while, you'll realize the two best factors. So 36 times 3, the square root of 36 is 6 times the square root of 3. 3 times the square root of 200. So we have a coefficient 3. We're going to break 200 into 100 times 2. The square root of 100 is 10. 10 times 3 is 30 square roots of 2. We have 1/2 as our coefficient. We see 4 times 7. We're going to take the square root of 4, which is 2. We can see these 2's cancel, leaving us with a coefficient of 1 times the square root of 7. 12 is 4 times 3. And now we have a squared times a squared times a squared times b squared. And let's extend the radical. We're going to take the square root of 4, which is 2. The square root of a squared is a squared is a, the square root of a squared is a, and we have the square root of b squared, which is b, and we're left with radical 3. Now let's put our a's together. A to the third times b to the first times the square root of 3. And 98. It may have taken you a few minutes to figure out 98, but it is 49 times 2. And then we have a squared times a, b squared times b. We're going to take the square root of 49, which is 7, the square root of a squared, the square root of b squared, and we're left with radical 2ab.